All right. So let's know how much does an 80-kilogram person weigh on Mars, Moon, Earth, right? So notice here, the weight is a function of mass times gravity, right? So our weight is going to depend on the planet we're on. And so basically it's going to be, I'm going to put a little subscript here, I, right? I is just going to be dependent on the planet. So our weight is going to be equal to 80 kilograms times whatever that G is for that particular planet, right? So let's make a table here. We'll put planet. I guess technically the moon is not a planet. Put location. It doesn't matter. All right, so we've got Mars, Moon, and Earth. And the mass is constant, right? I just want you to recognize, I should change this to 3 significant figures. I hate writing just a decimal point like that. And then gravity is what varies on each planet, right? On Mars, we've got 3.93. I'm just keeping the units up here at the top. It makes it just easier to. We've got 1.63 on the moon, and for Earth, we're using 9.80. And so the weight is in newtons. If you just, let me just make an, well, let me just do the multiplication. So if you just do the multiplication, you get these numbers, right? 80 times G. So we've got 314.4 on Mars. For the moon, we've got 130.4. And then on Earth, we have 784. And we're going to round these. So note 2 sig figs. So here on Mars, we're going to round it to 310 newtons. And then on the moon, we'll go to 130 newtons. And then on Earth, 780 newtons. Right. So you can see that this is well, there's also directly proportional to the gravitational acceleration, right? Let me just do a quick calculation here. I think, what's the moon? Is that 9.8 divided by 1.63? Yeah, it's about 6 times the difference, right? So that's about 6 times the difference. So this is 6 times the difference, right? You weigh 1/6 less on the moon than on Earth. See, 1/6. And Mars is closer to, well, it's closer to half, I guess. 9.8 divided by 3.93. Yeah, 2.5 times. So you weigh about 2.5 times less on Mars than you do on Earth. And you can see the, right, the proportion, basically whatever this ratio is, that ratio is. Because the mass is constant, right? So this is what we mean by directly proportional. Weight is directly proportional to the gravitational acceleration on a planet for a given mass. Any questions about this example, or either the other two if you had a question the other day and didn't get a chance to ask it? All right, because otherwise I'll move on to more exciting examples here. Let me, you know what, I'll put this so we have, in case you're still copying the table down. All right, let's see, this one is, the sun is a distance of 1.5 times 10 to the 8th kilometers from the Earth. How long does it take sunlight to reach the Earth if light moves at 3.0 times 10 to the 8th meters per second? Let me write down what's given first, and let's look at our equation too. Remember, we have the average speed is distance over time, right? So we want to find time, right? So distance is going to be, or sorry, we want to find time. So time is just distance over average speed, right? Let's write down what we know. We know the distance, 1.5 times 10 to the 8th kilometers. And we actually know the average speed, right? Sunlight travels at 3.0 times 10 to the 8th meters per second. I should make my exponent numbers a little smaller. That's 10 to the 8th. It's an exponent. Now, what I want you to notice on here is I want you to notice units. Right? These are not the same. If I divide kilometers by meters, I'm going to get kilometers per meter. The meters aren't going to cancel. So I need to convert one of these into the other. You can work either way here. But what I'm going to do is I'm going to convert the distance from kilometers to meters. So convert one distance to the other with respect to units. So D is 1.5 times 10 to the 8th kilometers, right? This K here, this is times 10 to the 3rd, right? I'll write it over here. This is the same as 1.5 times 10 to the 8th times 10 to the 3rd meters. This is basically saying you're multiplying this number by another 10 or another 3 tens, right? So this is going to get bigger, right? I'm adding more tens to this number. So my distance is going to be, when you multiply exponents together, or when you multiply numbers with exponents, you add them, right? And you can figure this out by, you can look at, was there a question?
No, I just said it's 11 power.
Yeah. So this is like saying 1.5 times 8 tens. And then this is saying you multiply this again by 3 tens. It's the same thing as saying 1.5 times 11 tens. So 1.5 times 10 to the 11th meters. That's our distance. So now we can write time is equal to distance over speed or average velocity, which is, or average speed. Oh my God. 3.0. I was just talking about velocity in my last class. When you do the division here, you get, let's see. If I, let's just look at the numbers here. Let me cancel my units. 1.5 divided by 30 is going to give us 1/2. And then 10 to the 11th divided by 10 to the 8th is just 10 to the 3rd. So this is division of exponents. You just subtract, right? This is like saying I'm multiplying this number by 10, 11 times, but then I'm dividing it by 10, 8 times, right? So my net multiplication is 3. This is in seconds. So I'm going to write this out in decimal form. Our time equals, right, this times 10 to the 3rd. So 1, 2, 3 seconds. And I need to figure out my significant figures here. I basically got 2 in each of these, right, these measurements. So my answer is going to be written with a bar over the 0 here. This is my time in seconds. What does it want in, oh, yeah, that's just me converting. So the other thing I can do here is I can convert this to minutes, right? I can say 500 seconds times, I want minutes, right? I have seconds. 1 minute is 60 seconds. So I just divide this by 60 and I get 8.333, etc. minutes. Oh, see, this is where the bar gets confusing. This equals 8.3 minutes. This is the problem. I didn't occur to me until I just wrote it, but the bar is sometimes used to, well, a lot, it's very much used in math to denote a repeating number, right? And here we're using it for significant figures. This is not a, well, this is not a repeat. It technically is a repeating 0, but this is to indicate 2 significant figures. This is to indicate repeating. I'm just going to scratch this out because it's just going to be more confusing for people when they see that. So 8.3 minutes. The other thing you could have done here, I'm going to draw a faint line here. Instead of converting the distance from kilometers to meters, we can convert speed from meters per second to kilometers per second. Right? So that means that V bar here, let's see, what do I have? 3.0 times 10 to the 8th meters per second. Now, this is just like a normal conversion, right? I'm looking at this, I say, okay, I want kilometers per second. 1 kilometer is 1,000 meters, right? And this gives us, so now notice we're dividing this by 1,000, which is 10 to the 3rd, right? So we're multiplying the 3.0 by 10 8 times. And then we're dividing it by 10 3 times. That's the same thing as getting 3.0 times 10 5 times, right? And now the units are kilometers per second. So this is what V bar would be in kilometers per second. And now you can solve for time again. Time is just, well, let's see, it's up here. Distance over average speed, right? So what's our distance? Our distance now is in kilometers here. 1.5 times 10 to the 8th kilometers. And now our average velocity is in kilometers per second. So I've got 3.0 times 10 to the 5th kilometers per second. Notice you get the same thing here. We've got 1.5 divided by 3 gives us our 0.5. And then we've got 8 tens divided by 5 tens. That leaves 3 tens. Oop. I was going to write a 3 there. 10 to the third. And this is now in seconds still, right? Because the units canceled out. So this is why it's important to keep the same units of the one that cancels, or to cancel them out from each other, because you can't cancel kilometers and meters. They're off by a factor of 1,000. So this number obviously is going to be, again, 500 seconds, right? So this is just showing you can do this either way. You can convert the distance from kilometers to meters, like we did on top, or we can convert the speed from meters per second to kilometers per second. And either way, you should get the same answer. Any questions about this this problem here? As usual, the more in depth you get, the more ways there are to do something sometimes. All right. Okay. This one's back to average speed. This is this is now more of a thought problem. A car has an average speed of 80 kilometers per hour for 1 hour. Then it has an average speed of 90 kilometers per hour for 2 hours. What was the average speed for the entire 3-hour trip? So let's, first what I want to do is I want to sketch this out, but I want to figure out what the, from my own knowledge, I want to convert this to miles per hour and see what this is. Oh wait, that's kilometers per hour. Yeah, so it's about 50 to 56 miles per hour. So the thing is that the car is going along for 1 hour. And in this region, 1 hour at 80.0 kilometers per hour. Then it travels along for 2 hours at 90 kilometers per hour. What's the average speed for the entire 3-hour trip? There's a few ways to do that. I'm going to show you basically the simplest way. Remember our triangle for speed, right, which we just covered. V bar is d over t. The first thing we're going to do is we're going to find out, we don't know the distance that each one's traveled, right? So let's look at this. We want to find the average speed for the overall trip. So V bar is d over t, right? We don't know the total distance. We weren't given any information about the total distance, but we do know the speed and the time for each segment of the trip. All right, so this is segment 1, and this is segment 2. These are supposed to be Roman numerals. They didn't come out that way. So the first thing I can do is I can figure out the distances traveled for each of the segments. So for segment 1, find d1, right, distance 1. And the distance is just average speed times time. So d equals v bar times time. I'll put the little subscript I for section 1, right? Segment 1. And what is this? This is 80 kilometers per hour. Oh, and one thing you do want to do is you want to check, right? The information we're given, kilometers per hour and time in hours, that's all appropriate, right? For 1 hour, right? This gives you 80.0 kilometers. I've got to watch my significant figures here. I'm not going to do any rounding to the end. We've got 80.0 kilometers per hour times 1.0 hours. Now, obviously, 80 point kilometers is the same as 80.0 kilometers, but that's our distance. 80 kilometers. Our second distance, right, segment 2, we can write the similar equation. The second distance is equal to the average speed in the second portion of the trip times the time of the second portion of the trip, right? And that's just equal to 90.0 kilometers per hour times, we were going for 2.0 hours. So this is 180 kilometers per hour. Or sorry, kilometers. Oh my God. I should cancel these units here so I don't confuse myself. 180 kilometers. So the second portion of the trip, we travel 180 kilometers. The total trip distance is D1 plus D2. And we'll just call this distance total, right? So this is equal to, well, we've got 80 kilometers plus 180 kilometers. Now, you can see here that even if I do carry through with 3 significant figures, I'm going to wind up, again, I'm going to wait and round to the end, but it's really kind of up to you how you want to do this. The distance is technically only good to 2 significant figures. So we'll show that in a minute here. This is your total distance is 260 kilometers. So what I was waiting for is you want to make sure, okay, what do you got? What do these 2 numbers come out to be? Okay, yeah, 2 significant figures, we can write these down. Our final distance should have 2 significant figures, 260 kilometers, right? Because each of our independent multiplications up here gave us 2 significant figures, right? So I could make a little note up here. So 80 points with 2 sig figs, and this is 180 with 2 sig figs. All right, we've got 2 sig figs here. We still haven't gotten what we need, right? This is the distance, the total distance. We want to know what was the average speed for the entire 3-hour trip. So now we finally can figure out the average speed for the trip is the total distance, right, divided by the total time. So here we've got 260 kilometers divided by 3.0 hours. Now notice the hours, right? We've got 1.0, 2.0, those, or we're given it was 3.0, it adds up to 3.0. And this gives us 86.666, etc. I'm not going to use the bar, kilometers per hour. So our average speed is now, looking at two significant figures, 87 kilometers per hour.
Sorry, can you explain why it's just two significant figures in the answer again? Aren't there three in the original question? Wouldn't 80.0 be three significant figures?
Well, yeah, 80.0 is three significant figures, but even if you had divided by, so here we've got two significant figures because the distance, in this case, we multiplied each of these by two significant figures. So we wind up with 2. Even if we carried through 3, in the end, we're still dividing by 2, right? That's kind of why I put it out like that, just to show you that, you know, in the end, you still wind up with two significant figures because you've got two significant figures in the time measurement.
Yeah, got it.
Yeah.
Excuse me.
Yep.
But in the line, under the line, it says 1 hour, it's only one significant figure. So 2 hours, it's one significant figures. It's now 1.0. The line where is 1 hour at 80.0 kilometer per hour.
Oh, here?
Yeah.
Oh, I'm sorry. The numbers are, I'm taking them from up here.
Oh, okay.
Yeah, it's 2 hours. Here, let me rewrite it here. 1.0. I'll make my notes a mess just to give you the satisfaction of having the 2.0. It was given in the problem statement. So again, go back to the problem statement. Make sure you're carrying through the significant figures that you're being.
It looks so long. I mean, the calculation, it's so many calculation. I just simply did 80 plus 90 and plus 90, and the result I divide by 3 and I get the 86.6.
Oh, you did 80 plus 90 plus 90.
Yeah.
Yeah, that's a more complicated way to do it. You could say you went 90 for, you break it down, it's basically a weighted average.
Mm-hmm.
Yeah, that's what you did. 2/3 of the trip. It's like saying 2/3 of the trip you went 90, 1/3 of the trip you went 80. That's all. Yeah, but this is, you know, this is the basis. This is basically what's happening, right? You're calculating the distance for each one of those. And it's really not that long of a calculation. I always make it longer than it really needs to be, just because I'm writing things out and explaining it as I go. All right, so that's example 5. We should be able to get through. Oh yeah, we'll get through the next 2 here. Example 6. Let's see. A rocket moves through space at 11,000 meters per second. At this rate, how long would it take in hours to travel the distance from the Earth to the Moon, which is 380,000 kilometers? Yeah, so let's just write out what we have here. Remember, we know that the triangle rule, or from our triangle, V bar is distance over time. So we want time, right? T equals D over average speed, right? Do we have that information? We have D equals 380,000 kilometers, and V bar is 11,000 meters per second. I'm going to leave the comma out because it's going to get mistaken as a 1 at some point. Again, notice the units, right? Kilometers and meters. I'm going to rewrite the distance, I guess. Let's see. K equals 10 to the third. Right, so, oops, 380,000 times 10 to the third is basically, right, 380,123 plus another 123. I'm going to rewrite this in scientific notation so that now you can see why we use scientific notation to save space, particularly in things like when you're dealing with really big numbers or really small numbers, right? 3.8 times 10 to the what? We've got 1, 2, 3, oh, sorry, 1, 2, 3, 4, 5, 6, 7, 8. And you could have done that here too, right? 1, 2, 3, 4, 5 plus 3 is 8. 3.8 times 10 to the 8th meters. Now, I'm going to do something here with the time. We want the time in hours, right? So what I want to do is I want to show you, I'm going to write T equals D over V bar. It's a D. So we've got 3.8 times 10 to the 8th meters divided by V bar is, 11,000. And this is going to give us a pretty repeating value. So we've got 34, 54, 5. So 34,545.45 ... It just continues to repeat. Seconds. Now, I want to know the time in hours. So let me just do a quick side calculation here because I want to make sure. Divided by 60. Divided by 60. Oh, it gives us pretty close to the same thing. What I'm going to do is I'm not going to round my time yet. This is the equivalent of taking your calculator and just doing, continuing to go do the math. And when you do calculations in, say, a spreadsheet or on a computer or something, the computer carries through all the digits as far as it can until the end. And then in the end, it rounds to the, in the end, it's up to you to sort of round the significant figures. I was going to try to make the point with the last problem, but that wasn't really a good problem for it. So now if I'm going to take this, I'm going to take and convert this to hours. So let's do in over here in case 1, I've got 34, 54, 5. I'm going to stop it there. This is seconds. And I want to get hours, right? 1 hour is how many seconds? You guys know?
3,600.
Right. All right, so this I'm going to divide by 3,600. So 34,545 divided by 3,600. Here I've got 9.59, I'll round it to 6, right? This is hours. So my time is 9 points. Now here's where I look at it, I'm saying, okay, I've got 11,000 meters per second, 380,000 kilometers. I really only got 2 significant figures in both of these measurements. So I'm going to report this as 9.6 hours. I'll write out hours. For some reason, I don't like to see an H by itself. I don't know what that is. Now, the other route I want to show you here, this is not another route. This is just, I want to show you what happens if I had rounded this early, right? I would have gotten, so rounding early, I would have gotten 35,000 seconds, right? And then that would have been 35,000 seconds times 1 hour over 3,600 seconds. And this is going to give me 9.722. So this would have given me a time equal to 9.7 hours. So you can see here, the only point here is that depending on where you round, you could wind up with a different answer. So for multi-step problems, you typically want to hold off and round at the end, right? You don't want to round each step. So if I had like 3 or 4 steps, I could have easily wound up with some final answer that was a lot different than what the actual answer would be. So this is the way we do it, right? Typically, round at the end of calculation. So take into account, all the different steps, because we could have converted into time in one shot up here. I could have just multiplied this whole thing or divided this whole thing by 3,600. And if I'd done that in my calculator, I would have gotten the 9.596 hours, right? Which I've rounded to 9.6. All right, so I think this is all we have for motion. There's one more free fall problem, or for average speed. Now we're looking at free fall again. Are there any questions about example 6? I think I carried through all my numbers. All right. Now we have an object is observed to fall from a bridge. It strikes the water below 2.5 seconds later. What velocity did it strike the water? With what velocity did it strike the water? I felt like I was forgetting something. All right, so let's draw, I don't know, this is the side of the bridge. Right, and there's water down here. Water. Bridge. And I see this object fall, right? And the only information we're given is that the time from when I see it fall to when it hits the water is 2.50 seconds. With what velocity did it strike the water? So I know that on Earth, we're on Earth. I don't know of any bridges and water on any other planet. My acceleration is equal to that of gravity, right? And I also know my acceleration equation is final speed minus initial speed over time, right? So now what I'm trying to figure out here is I'm trying to figure out the final velocity, right? Find VF. And the known information is what? We've got, let's see, T equals 2.50 seconds, right? And G equals 9.80 meters per second squared. That's our acceleration. We've got these two velocities. Oh, you know what? I forgot. In this class, I'm using an O. We don't know VF. Oh, VO in this case, what do you guys think VO is, the original velocity?
0.
0, right? Because it's starting, it's it's dropping from the bridge, right? Someone's dropping it off, or it's sort of, tumbles off the bridge. I don't know. So its initial velocity is 0. And we're using meters per second up here. Or the units are SI. So now what I'm going to do is I'm going to rearrange this equation. I can take and multiply both sides by t, or I can use my triangle. Let me use my triangle rule here. At some point, we're going to have to do algebra with this one, so it doesn't really make life easier. Right? If we want to find VF minus V naught, that's just G times T. So we've got G times T equals VF minus V naught. And again, I'm not using multiplication sign because it's just going to get too confusing. This is an implied multiplication. Now, if I'm subtracting V naught over here, fortunately V naught is 0. But if I wanted to solve for VF, right, I would just add V naught to both sides, right? Because this is an equation. The way algebra works is if you do something to one side of an equation, you have to do it to the other. So if I add V naught over here, right, I'm going to wind up with V naught plus GT equals VF, right? Because here I've got a plus V naught, here I've got a minus V naught, so they're canceling out. So this is what VF is. Let me just rewrite it down here. VF is just equal to V naught plus GT. So this is interesting. I just want to point this out. This is telling you your final speed is equal to whatever your initial speed is plus the acceleration times the time. So technically, you could be given something like it falls off the bridge, or it passes the bridge at a speed of 5 meters per second, right? Now we know that V naught is 0 here in this problem. But this makes sense, right? You're saying the final speed is equal to whatever the initial speed was plus the speed it gets from accelerating over a certain amount of time. So then we wind up with VF equals, let's put the numbers in now. We've got 9.80 meters per second squared times 2.50 seconds. And VF here is going to be equal to, this actually turns out to be right on, I think. Let's see, 9.8 times 2.5. Yes, 24.5 meters per second. So notice the seconds here are canceling. And then you're left with the final speed is 24.5 meters per second. And remember, we're using 9.8 meters per second squared as an exact acceleration. So we wind up with 24.5 meters per second. That's how fast it hits the water at if it takes 2.5 seconds to fall from the top of the bridge going at, well, starting off at 0 meters per second. All right, I wasn't sure how far I'd make it. I was going to start Newton's third law, just start mod 5, but this is basically the end of mod 4 right here. So I think what I'll do is I'll just end. We only got 2 minutes, so if there's any questions about anything, you can ask me about mod 4, and then we'll start mod 5 tomorrow, which is Newton's laws. Yeah, today's Wednesday. All right, so everyone, thanks for
Thank you.
thanks for being on and
Thank you.
participating, and